Welcome to this explainer. Okay, today we're going to do something highly visual and honestly pretty cool. I want you to imagine that we're booting up a specialized physics heads-up display, a HUD, right over your field of vision. With this system online, we're going to completely visualize the invisible mechanics of the universe. We're talking about the hidden forces that govern absolutely all motion around us. To get our system calibrated, we've got to start with one fundamental question. What exactly causes an object to accelerate? Now, in physics, we spend a lot of time studying the motion itself, right? Velocities, distances, times. But today, we're focusing on the actual cause of that motion. When an object accelerates, its velocity changes. And that change, it's always driven by an invisible push or pull from another object. Before we start tracking these pushes and pulls, we need to quickly establish the basic language of our HUD. We'll be using two types of physical quantities. First up, scalars, like mass or temperature. A scalar is simply a magnitude. It's just a single value with a unit, like kilograms. It doesn't point anywhere in space. But then we have vectors. A vector absolutely must have both a magnitude and a direction. Force is a vector. Think about it. If you push something, you have to push it in a very specific direction. System initialization complete. Here's our quick agenda for today. 1. Inertia. 2. The F equals ma equation. 3. Specific forces. 4. Free body diagrams. And finally, 5. Newton's third law. Let's jump right in. Module 1, Inertia and Equilibrium, the baseline states. So what happens when the net force on an object perfectly balances out? Consider this massive natural rock formation. Despite its incredible size and the fact that the gravitational pull of the entire Earth is trying to bring it down, its velocity isn't changing one bit. It's at rest, and it stays at rest. Why? Because all the different pushes and pulls acting on it cancel each other out perfectly. The net force is exactly zero. In physics, we call this a state of equilibrium. And that brings us to Newton's first law. It states that if no net force acts on a body, the body's velocity simply cannot change. It cannot accelerate. But there is a slight catch here. This rule only applies in what we call an inertial reference frame. The solid ground beneath us, that's generally a great inertial frame. But if you were trying to measure forces from, say, a rapidly spinning carnival ride or a car slamming hard on its brakes, your reference frame would actually be accelerating. In those non-inertial frames, Newton's laws don't quite work without inventing some fake, fictitious forces to explain what you're seeing. So for our HUD today, we are going to stick to the solid ground as our inertial frame. Moving to Module 2, the core equation, F net equals ma. Now when forces don't balance out, we need a master equation to figure out what happens next. Let's look at this glowing holographic centerpiece of Newtonian mechanics, Newton's second law, F net equals ma. The net force on a body is equal to the product of that body's mass and its acceleration. This beautifully simple string of characters dictates exactly how motion changes across our entire universe. Let's break down these variables. Mass is our scalar. It's an intrinsic characteristic of a body measured in kilograms. Force and acceleration, however, are our vectors. If we applied a net force to that intrinsic mass, it dictates the exact magnitude and the exact direction of the resulting acceleration. To put it in perspective, in a standard metric system, a force of 1 Newton is exactly what it takes to accelerate a 1 kilogram mass at 1 meter per second squared. Module 3, a catalog of specific forces, activating the targeting system. Scanning our everyday environment, our HUD has locked onto 4 primary forces that we'll be tracking today. As we analyze different situations, we'll constantly be looking out for gravitational force, normal force, tension, and friction. Let's explore how a couple of these forces interact in the real world. First, we have the gravitational force. This is the constant downward pull of the Earth on an object's mass. The actual magnitude of this force is what we typically call weight. But think about it. If gravity is constantly pulling us down, why aren't we all just accelerating straight through the floor? Well, that's thanks to the normal force. When you press against any surface, it deforms slightly and actually pushes back against you. This force is always perpendicular to the surface. It is quite literally what prevents you from falling into the center of the Earth. Next up, let's contrast tension against friction. When a cord or rope is pulled taut, it exerts a tension force on whatever object it's attached to. This force is always directed away from the object, straight along the cord. On the flip side, we have the frictional force. If you try to slide an object across a surface, friction is that parallel force from the surface that actively fights back and opposes that sliding motion. Module 4, Mastering Free Body Diagrams, Processing Visual Noise. Real life is incredibly full of visual noise, so we need a reliable way to process all that chaos into clean, actionable physics data. Here is our systematic 4-step protocol for creating free body diagrams. First, identify the specific body you want to analyze. Second, strip away the entire surrounding environment and just represent that body as a single dot. Third, draw all the external force vectors with their tails anchored directly onto that dot. And finally, step 4, superimpose a standard x and y coordinate axes right over it. Now the really crucial part is what happens next. Remember, F equals ma is a vector equation, which means it can be broken down. Once our axes are locked in, we map our vectors, and we process the x and y dimensions completely independently of each other. The forces pulling horizontally along the x-axis, they have absolutely zero effect on the acceleration along the vertical y-axis. It's like two separate worlds. So we write completely separate component equations to solve for our unknown variables. Let's apply this to a classic physics scenario, a heavy block sitting on a tilted ramp. If we try to use our standard straight up and down, horizontal and vertical axes here, the math gets incredibly messy fast because the block is accelerating at a weird angle down the ramp. But our solution to this is just so elegant. We simply rotate our HUD's coordinate system to match the exact incline of the surface. By tilting our axes, the x-axis now runs perfectly parallel down the ramp, which is exactly the direction the block is going to accelerate. This means the normal force points perfectly up the y-axis. Gravity, which of course still points straight down toward the Earth, now splits cleanly into two components, one component pressing firmly into the ramp and one pulling the block down the incline. It makes the math a breeze. Okay, let's move on to a second schematic. Imagine a sliding block resting on a totally frictionless table. It's attached to a taut cord that runs horizontally, goes over a pulley at the edge of the table, and drops straight down, where it's attached to a hanging block. So how on earth do we find the acceleration of a system like this? Well, we don't panic, we just follow our protocol. We draw two completely separate free body diagrams, one for the sliding block and one for the hanging block. The sliding block is accelerating along its x-axis purely due to the cord's tension. The hanging block is accelerating along its y-axis due to gravity fighting against that very same tension. And here's the magic. Because they're connected by the same taut cord, we can mathematically link their equations together. They share the exact same tension force and the exact same magnitude of acceleration. And finally, Module 5, Newton's third law and symmetry, the interaction of bodies. Let's reveal the beautiful underlying mathematical symmetry of how objects physically interact in our universe. Imagine a book leaning against a heavy crate. The book is definitely pressing against the crate, but at the exact same time, the crate is pressing right back against the book. Newton's third law dictates that these two forces are fundamentally and permanently linked. The horizontal force of the book pushing on the crate and the horizontal force of the crate pushing back on the book are perfectly equal in magnitude, but they point in exactly opposite directions. Here is the formal definition. When two bodies interact, the forces on the bodies from each other are always equal in magnitude and opposite in direction. Practically, this means that every single force in the universe is actually just one half of a perfectly balanced interaction pair. Think about that for a second. You literally cannot touch something without it touching you back with the exact same amount of force. Which leaves us with a final, slightly mind-bending question to wrap up our explainer today. If every single force in the universe has an equal and opposite pair, how does anything ever manage to accelerate? Like, if I push a heavy cart with 50 newtons of force, and it pushes me back with 50 newtons, shouldn't they just cancel out to zero? Think deeply about how we draw our system boundaries, and which specific forces apply to which specific free body diagram. Motion emerges from these beautifully balanced rules, and how you define your target changes everything. Until next time, keep your HUD active and keep questioning the mechanics of the universe.